And this is a super important problem about AlphaFold, and there's so much yet to do, although many people think it's all been solved by people.
Thank you very much, Jotun. I think this is kind of the fourth or the fifth time that I'm here and visiting you. It's always
some new friends.
yes, because you're moving. It's always a pleasure to be here. So this is the topic I will talk about today. So I will talk about AlphaFold, and so I will try to explain how there's actually a very nice probabilistic explanation behind the first initial success of AlphaFold, and it's quite an under-recognized role that probability plays. And that's today what I want to talk about today. And so this probabilistic underpinning in the initial success of AlphaFold is probability kinematics, and that will be central to the talk today. So let's be precise. And so what is this about? And let's try and boil it down to the kind of like the mathematical essentials. So proteins are biomolecules that consist of amino acids. These come in 20 different types, and it's very easy to get to the sequence of a protein. So it's basically just a sequence of symbols. And so this sequence of symbols encodes a chemical structure. But knowing the chemical structure is not enough to know what the three-dimensional shape is of a protein. That's actually quite complicated, and has been an open problem for more than 50 years until it was declared a solved problem, resulting in a Nobel Prize last year. So what is the problem? So given an amino acid sequence S of length L, we want to predict the three-dimensional structure of a protein. Boil it down to the essentials. What we want to do is we want to predict a matrix which consists of L times 4 atomic coordinates. So these are 3D atomic coordinates. And these are the coordinates of the N, C alpha, C, and C beta atoms. So there are more atoms involved, but if you get these guys right, then you can predict the rest of the positions. So that's kind of like the problem boiled down to its essentials. We are Bayesian, we're probabilistic, so we want to have a nice probability distribution. So what we're interested in is the probability of the structure given the sequence, and that's equal to the likelihood here times the prior and a normalization factor. So that's proportional to this likelihood, the probability of the sequence given the structure times the prior over the structure. So that will be our ultimate perspective. So we're here in November 2020, and this is a press release of the CASP people. So CASP stands for Critical Assessment of Protein Structure Prediction. This is like the Olympic Games of protein structure prediction. And there's a very dramatic press release, artificial intelligence solution to a 50-year-old science challenge should revolutionize medical research. And so this happened in November 2020. So this 50-year-old problem was officially declared solved by this initiative, the CASP initiative that evaluates the efficiency of these predictions in a double-blind method. And so more specifically, they write today, on a Monday specifically, the researchers at the 14th community-wide experiment on the critical assessment of techniques for protein structure prediction, and that's CASP 14, will announce that an artificial intelligence AI solution to the challenge has been found. And that is, of course, the solution is, of course, AlphaFold 2 by DeepMind. And this is quite an accomplishment. So this is an example that was shown around that time. So this here is a protein with more than 2,000 amino acids, 10,000s of atoms, and you can see that even for enormous proteins like this, we can have fairly good predictions. So it's indeed an enormous breakthrough. The last year, this resulted in a Nobel Prize. So the DeepMind people and then also David Baker, they shared the Nobel Prize for solving the protein folding problem, the protein structure prediction problem. So this was AI's big Nobel moment, the first one, actually. So they got the Nobel Prize in chemistry for this. And this was not the only prize for AI, but in the same year, also last year, so John Hopfield and Geoffrey Hinton, they also got the Nobel Prize for developing artificial neural networks, and they got the Nobel Prize in physics for this. So strange, yeah, it's quite unusual prices, basically. If you see that this is basically computer science and got the prize in physics, and this is bioinformatics, and it got the Nobel Prize in chemistry. Okay, so let's take a look at what AlphaFold 2 is doing. So AlphaFold 2 does end-to-end prediction of protein structures. So that means that here you have an input sequence, and to a number of neural network layers, and then you have a 3D structure that basically comes out. So they call this end-to-end prediction. That's important because later on we will take a look at AlphaFold 1, and we will see that this was not end-to-end prediction. There was actually something else going on. So, but here we basically have the input, a large number of layers, of neural network layers, and then we have an output. And specifically, you see these two blocks here. So you have the Evo former, and you here have the structure module. So up to here, everything happens with respect to protein sequences and with respect to 3D, with respect to distances between atoms. While here, we actually already built 3D structures. So we have amino acids in space, and the neural networks will act here on these 3D positions. And then here we have the final structure. So what is the general idea in this method? So the general idea is essentially, can we predict which amino acids are close together in space? And why is it possible? Well, suppose that you have an amino acid sequence and you want to predict the three-dimensional structure. So the first thing that you do is you get a lot of related sequences, so proteins that belong to the same family. And if you take a look at the 3D structure, sometimes amino acids, they will be close together. Now, if they are close together, then they will also mutate together. So by investigating the pattern of mutations, you can note that, well, every time that this amino acid mutates, this other amino acid mutates in tandem. And if you pick up these types of patterns, then you can actually infer the three-dimensional structure. So this was originally done, for example, here, this publication, classic publication by Marx et al. In 2011. This was done with smart maximum entropy statistical methods. AlphaFold essentially did it with neural networks. And this was also not new. We have, for example, here, this publication by Wang et al. This is a group in Chicago, the Toyota Institute. And in 2017, they also used neural networks to pick up these types of patterns. So that's essentially what these methods are doing. They are picking up which amino acids are close together, and they investigate these correlated mutations. So first with statistical methods, now of course with neural networks. So there were a couple of innovations or a couple of key ideas, and so AlphaFold 2 was based on the attention. AlphaFold 1 was not based on that. Attention mechanism is, of course, something that we know very well from ChatGPT. I'm not going to go into detail here because this is not about the attention mechanism. But basically, the attention mechanism was extended to finding out which amino acids are close together, and the attention mechanism was extended to considering triplets of amino acids. So that turned out to be a very good idea. So this was called triangular self-attention. And on top of that, there was also an attention mechanism that worked not on sequences or on symbols, but on 3D coordinates, and that was called invariant point attention, IPA, and that basically made the attention mechanism rotation and invariant, and made it possible to work on 3D structure. There was something that was also worked on before by, for example, the group of Max Welling, and you have this publication here in NeurIPS in 2020 that predated the AlphaFold publication. And so in general, these types of things, so making these networks rotation and translation invariant, that fits within this very classical statistical discipline, the discipline of statistical shape analysis. And the co-author here, or the co-author of this presentation, Kanti Mardia, has been working a lot on this topic. But I want to take you back to AlphaFold 1. I want to take you back to 2018. We are at CASP 18, so that's the CASP before the problem was declared solved, and we have another dramatic message from the CASP people. So this time on their message board, it was not a press release, but it appeared on their message board. And they said, CASP 13 this year has observed unprecedented progress in the ability of computational methods to predict protein 3D structure. The reasons are not yet fully clear at that time, but all this, including, of course, the results, will be discussed at the meeting. And of course, we all know what was going on at that point. DeepMind entered the competition, and they basically had unprecedented progress. They blew all of the academics out of the water, and that led, for example, to this announcement here in Science. So Google's DeepMind ACES protein folding. So this is AlphaFold 1. We're in CASP 13. AlphaFold 1 and AlphaFold 2 are very different beasts. They're built on different principles, although they both attempt to predict which amino acids are close together in space. They share that. So this is a picture from the AlphaFold 1 publication that appeared in Nature in 2020. And this was called Improved Protein Structure Prediction Using Potentials from Deep Learning. So this is not end-to-end prediction, but this is what actually makes use of potential. And it's about these potentials that I want to talk, because they have a very nice probabilistic interpretation. So this here is the overall pipeline. So again, you have the sequence and the multiple sequence alignment, so sequence and related sequences. You pull them through neural networks, you get an idea of which amino acids are close together. You combine that with some predictions of angles in proteins. Using these two ingredients, you're going to make a potential, and your final prediction will result from minimized potential. And before we go on, let me introduce you to a bit of notation so that everything is kind of is clear. So I sent these slides to Kanti Mardia, who's of course a statistician, and he pointed out, like, Thomas, you need to kind of be precise about your notation. So here's a slide about the notation. So S is our protein sequence. This is basically something like a vector of one hot representation, so concatenation, and the length is 20 times L, 20 amino acids. L is the number of amino acids in the protein. We have our multiple sequence alignments. These are sequences of related proteins. You get this from database searches. This is an M times 20 by L matrix. X are our atomic coordinates. This is a tensor. L, the length of amino acids of the protein. 4, these are the number of atoms we want to predict per amino acid. And then, of course, you have the 3-dimensional coordinates. So the 4 atoms are N, C alpha, C, and C beta. We neglect a couple of other atoms, but basically, if you get these right, you know you can infer the positions of the other ones. There's a lot of details that we are ignoring here. We assume ideal bond angles, ideal bond lengths. We assume that another dihedral angle is always equal to 180 degrees. We ignore the side chain atoms, and we can do all of that without loss of generality, just to keep the story simple. So then we have the phi and psi. These are vectors of dihedral angles. So there are angles that describe protein structure, and I will explain immediately what that means. And then we have D. This is a distance matrix. So this tells you which amino acids are closer to which other amino acids. We're only going to use one atom per amino acid. So we're not going to involve all atoms. We're just going to use one, and that's the C beta atom. So this is kind of a representative atom that tells you approximately where an amino acid is located. So if I will talk about D, it's an L by L distance matrix that encodes the distances between these C beta atoms. Now, what is very important, and this is a key point, that is that if I give you the dihedral angles, then I can calculate the distances. So the distances, the positions of these atoms that we're interested in, all these atom positions are completely pinpointed if you know the values of these angles. And that's going to become very important later on. And also NN, if you see that in an equation, that means neural network. So let's take a look at AlphaFold 1. So AlphaFold 1 is going to predict two things. So the first thing that it's going to do is going to predict these pairwise distances. So is an amino acid close to another amino acid? How far are they apart? And each amino acid will be represented by one single point. So you lose a lot of detail. The amino acids contain multiple atoms, but you're just going to represent it with one atom. So then you, for example, you have this protein over here. Let's consider this point here that represents one amino acid. And then you have all these distances. So these are the distances of this one amino acid to all the others. This is then represented in these distance matrices. This is the predicted distance matrix. This is the true distance matrix, and these red lines, they correspond to the distances of this amino acid to all the others. So you're going to obtain from neural networks are predictions related to these distances. So for every position in the protein, you will have a predicted distance, univariate distance to all of the other amino acids. And this is an example of what you get. So for this specific prediction, so you get probability distributions relating to the distance of one amino acid to all of the others. And you do that for every single amino acid in the protein. So this X, this is our structure. These are the atomic coordinates. And if you have X, then you can calculate D. Now, this is many to one. So there are actually several structures that can give rise to the same distance matrix. So again, because you only consider a subset of the distances. So keep that in mind because it's going to be very important. So only the C beta distances are predicted. So this is the first prediction that AlphaFold 1 will do. It will predict these distances. Then the second prediction that will be done, again with neural networks, and I will give you the details later on, are dihedral angles. So what are dihedral angles? So here you see an amino acid. This is one amino acid. This is the protein backbone. So this is the polymer part that keeps everything together. And this is the side chain. This is something that sticks out into space. So we're going to neglect this detail here because it's not important for the essential part of the story. So what we have here are two dihedral angles. So for every amino acid, we want to know the value of these dihedral angles. If we know the value of these angles, then we can reconstruct the protein in atomic detail. So nothing is missing. And what's a dihedral angle? Well, suppose that you look at these four atoms. So suppose that you look along this bond, and then the angle that is made between this segment and this segment, that's a dihedral angle. So it allows you to kind of create this chain of jointed segments and build the entire protein chain. So each amino acid corresponds to a pair of these angles. A dihedral angle goes from -pi to pi, and then again, so it's a circular variable. So one of these angles can be represented as a probability distribution on a circle. Since we have two of these angles, each amino acid can be represented as a probability distribution of two-dimensional torus. So that's the surface of the donut. And here you have an example of some probability of some points that are sampled from probability distributions on the torus. So this is a map that is 1-to-1. So if you know the dihedral angles, so you know a point on the 2D torus for every amino acid, then you can map it precisely to the three-dimensional structures. And this is 1-to-1. So each sequence of dihedral angle corresponds to one 3D form, and vice versa. And so we have L of these dihedral angle pairs, one for each amino acid. Is that clear? Any questions so far? No? Okay. So this is then AlphaFold's potential. So I will not go into detail here because I formulated it in a more, I think, more easy to understand probabilistic language later on. But I will just quickly walk through the essentials. So first, we have this potential here. So you have a probability distribution over the distances given the sequence and the multiple sequence alignment. This probability distribution is then turned into a potential by a simple log transform. Then you have a distance potential, and that's this one here. And again, you have a neural network, predict the distances, you have a probability distribution, you take a log transform and you turn it into an energy. Sorry, these are the two distance, this is the, so these are the distance potentials. So in here you have this potential here that predicts the dihedral angles of the amino acids. So these are the distance potentials actually. And so here you have the probability distribution over the dihedral angles. And again, log transform, you turn that into a potential. Then the total potential is the combination of these two potentials. So you have the distance potential, you have the angles potential, and then you have something here that keeps atoms from bumping into each other. This is a simple physical, it's not learned. So this is a learned potential using neural networks. This is a learned potential neural networks over angles and over distances here. Now, what is unusual here is that you have another potential here, which is a so-called reference potential. This is kind of a bit of a mysterious potential that is appearing here, and this is basically needed to tie the torsion angle potential and the distance potential together, and that will be basically the topic of my talk today. So here, this is what the AlphaFold people write about their potential. So we can train a neural network to make accurate predictions of the distances between pairs of residues. And so they convey more information about the structure than contact prediction. So distances rather than this amino acid is close to another amino acid. So using this information, we could construct a potential of mean force that can accurately describe the shape of a protein. And we find that the resulting potential can be optimized by a simple gradient descent algorithm to generate structures without complex sampling procedures. So you make this potential, and then you basically just predict structure by minimizing, using simple gradient descent, by minimizing this potential, and you get the predicted structure. Now, this is very interesting. So what is claimed that we have here a potential of mean force. And they refer to this reference number 4 here. And if you look it up, then you get this article over here. You get an article from 1935, that a famous article by about the statistical mechanics of fluid mixtures. So this is the justification that that AlphaFold gives for the construction of this potential. So but how do we go from this 1935 physics paper? It's kind of difficult to read, and how do we get from 1935 to 2020? So, and there is a very interesting story here that we can look at to understand what the relation is between this article from 35 that doesn't relate to proteins. It also doesn't relate to knowledge-based potentials or statistics, but actually it's a very physical description of a liquid. So how do we go from here to a solution to the protein folding problem to a neural network? So that's what we are going to take a look at now. So the AlphaFold potential combines a potential over angles with a potential over distances. So we have these two potentials that derive from neural networks. With fairly standard technology by that time. So we have these two potentials over angles, potentials over distances, and then they are tied together, they're combined using a third potential. And this they call a reference potential. So where does this construction come from, and how does it relate to this Kirkwood article from 1935 about the physics of liquids? Well, pairwise distance potentials they're actually used for a long time in the bioinformatics of proteins, and they were pioneered by a Austrian biophysicist called Manfred Sippel, and he published a seminal publication in 1990 about it. So, and they've actually been used for 3 decades. For AlphaFold used them. And so these so-called potentials of mean force that were developed for proteins, and they were in use since the 1990s. So it turns out that these potentials are not physical potentials of mean force in the very precise physical sense of Kirkwood's of the 1935 article. They're not really physical quantities. What they actually are an application of Bayesian reasoning, very smart Bayesian reasoning to this specific molecular system. And they follow a form of Bayesian reasoning. You could argue whether it's Bayesian or not, that is called Jeffreys conditioning or probability kinematics. Who has heard of probability kinematics or Jeffreys conditioning? It's very obscure, and I'm always very happy to kind of introduce people to what I think is like a very cool piece of Bayesian reasoning. And this is, of course, here Richard Jeffrey. He died in 2002, so he was a philosopher of statistics, a probability theorist. He didn't came up with it. I mean, the idea was around, but he really formalized it and turned it into a thing, so to say. And it's called Jeffrey conditioning or probability kinematics. So it's Jeffrey. Don't confuse it with Jeffreys, who is, of course, the very famous pioneer of Bayesian statistics in the first half of the 20th century. Okay, so what are we doing here? What are these potentials? So we are talking here about knowledge-based potentials. What's the idea? Well, a protein is a physical system, you have all things going on like hydrogen bonds, ionic bonds, hydrophobic effect, and so on and so on. And we have hundreds of thousands of examples of protein structures in databases. So the question is, how do we extract an energy function from this database of known 3D structures? So the thing that we're interested in, this is a quote from Sippel, the goal of these knowledge-based potentials is the extraction of an energy function from a database of known 3D structures which reasonably models the protein's solvent system. So that's what we're going to attempt. We're going to try to extract physics from statistics. So that's basically the game that we play. Can we develop a potential using what we know about proteins? So what I will tell you now is we'll go from some heuristics that are inspired by physics, and it seemed to work, but they are heuristics, and we're going to move from this heuristic approach to a well-justified method for formulating multi-scale probabilistic models that are based on probability kinematics or Jeffreys conditioning. So that's kind of the transition that we're going to make. So this here is the classic 1990 paper by Manfred Sippel. This is Manfred. He visited in Copenhagen years ago to discuss this. Actually, it was very nice to kind of talk to the pioneer of these potentials and find out that they have this very probabilistic interpretation. So this is a seminal paper. It's very influential. So this has more than 1,500 citations. It's very well known. If you Google PMF, potential mean force and proteins, you get 27,000 hits. A lot of these articles are bona fide physics, sort of really the hardcore thermodynamics and physics of proteins. But I think the most of these articles are actually about knowledge-based potentials. So they are about this heuristic way of extracting potentials from protein structures. So what is this trick? So how do you go from a sort of protein structure to a potential? Well, you start with Boltzmann's law. So this is the heuristic explanation. You will get another explanation later on. So we use Boltzmann's law, and that relates the energy of a microstate X. And in this case, our X will be a pair of amino acids. So think about the state as that. So it's just two amino acids that are close together or farther away from each other. So that's our simple state, right? So what's the probability of having two amino acids at a certain distance? It's 1 over a normalization factor, Z, times the exponent minus the energy of that system divided by kT, where K is the Boltzmann's constant and T is the absolute temperature. Now we can use the inverse of Boltzmann's law. We just reorganize these factors a bit, and we get the energy is equal to minus kT, the logarithm of the probability of finding that exact state. Let's say two amino acids at a specific distance, minus kT, the logarithm of this normalization factor. But of course, as usual, the normalization factor is intractable, but we cannot use it simply as is. So what are we going to do? Well, we're going to subtract a so-called reference energy. So we start with the inverse version of Boltzmann's law, and then we subtract a reference energy which is equal to this. So the reference energy is minus kT, the logarithm of the probability of that state according to some kind of reference situation, minus the kT of yet another normalization factor, Z. So PRX is the probability of the same state, but now according to some kind of other, let's say some other physical situation than an ordinary fold protein. You can think of it as a random packing of amino acids. So then we have an energy difference. So EX minus this reference energy is minus KT, the logarithm of this ratio. So the probability of finding that situation in proteins, and the probability of finding that same constellation, so that same situation in a reference state. And then you have this ratio of these two normalization factors. Now we assume that these two are, this term here is either constant or this thing is 1, so it disappears. We can neglect it, and we only get this term over here. So the logarithm of the ratio of these two probabilities. And so following Sippel, we end up with the total energy of a protein, and that's equal to this. So just sum over all pairs of proteins, and it's the logarithm of the probability of finding the two amino acids at a certain distance of each other, divided by the probability of finding two amino acids at that same distance in this reference state. And so what is the reference state? So first of all, what is this probability here? So the probability here in the numerator is derived from the protein data bank. And then the other probability is derived from a simulated random packing of amino acids. So typically, you assume that amino acids do not interact with each other, and you just random pack them into a ball in such a way that they don't overlap. So that would be your reference state. So you make the ratio of these two probabilities, and that gives you this, this energy. So again, typically only a subset of the distances are used. So you will only look, for example, at the C-beta distances. So it's a subset of the distances, not every distance, but you will take one atom that represents the entire amino acid. So this approach seems to work. So thousands and thousands of people have been using these types of potentials to simulate proteins, to investigate proteins, to identify disordered proteins, and so on. So this is something that seems to work to some extent. But why is this reference energy needed? So where does this come from? And how should the reference state be constructed? This used to actually be, there are hundreds of papers on specific states. So there's was a bit of an industry going on before AlphaFold of constructing better and better reference states. So let's turn now to the physics of liquids. So let's turn to Kirkwood, and let's see what's going on there. So we're going back to 1935. What is in that Kirkwood paper? So this is about the reversible work theorem for fluid mixtures. So, and this quantity over here, minus kT, the logarithm of this, this ratio of two probabilities, this is the reversible work required to bring two molecules in a solvent from infinite separation to a distance d from each other. And you see here, this is the probability of finding that distance in the liquid. And this here is the probability of finding that same distance in some kind of reference state. In this case, the reference state is very well defined. It's simply the ideal gas state. And this ratio here is called the radial distribution function. So this ratio of these two probabilities, G of D, and this can actually be experimentally observed using X-ray scattering. And this is called a potential of mean force. And this is a very physical, this is derived from physical principles, a very precise quantity. There is nothing controversial about it. It's extremely well defined and extremely used, commonly used in the physics of liquids. And now I can also explain to you what is the force and why is it mean. Well, here mean, of course, refers to averaging out. So you are going to consider two particles in a liquid and the influence of the surrounding liquid particles, so it's averaged out. So that's why it's called a potential of mean force. Now, applying this type of potential to liquids is kind of unwarranted. So first of all, applying Boltzmann's law to this to the protein situation in this case is kind of unwarranted because, of course, our probabilities, they don't come from a single protein. They come from a large collection of different proteins. So we can't just apply a Boltzmann distribution. It's a very different situation. The second thing is that we basically simply have two ratios of probability distributions over distances, but this similarity doesn't mean a vague analogy with the physics of liquids, with the physics of fluid mixtures, doesn't really explain why these potential means of mean force work, or why this would be warranted to use an expression like that. It's also not clear at all what we should use as a reference state. If in liquids, it's clear that we use the ideal gas state. In the case of proteins, it's not clear at all what we should use. And as I mentioned, so this used to be a publication bonanza. There are a lot of work on publishing better reference state. And then finally, also to be a bit more theoretical, so what we really want is the minimum, the Gibbs free energy. We want to minimize the free energy. And actually, even if this would be a bona fide potential of mean force, that doesn't mean that minimizing a potential of mean force in this case would give you actually the minimum Gibbs free energy. So there are a couple of very good arguments to be somewhat mistrustful of the application of these types of heuristic potentials. This is the classic paper on these potentials. Many papers that examine these potentials point out that they are ill justified, not well defined. This is a classic paper at Thomas and Dill. This appeared in 1996. This is just a quote. Our results suggest that current statistical potentials may have limited value in protein folding algorithms and wherever they are used to provide energy-like quantities. And there are many other articles like that. I think this is one of the famous ones. And actually, Sippel himself, Manfred Sippel, had also written articles like that. Well, these potentials are heuristics, but of course, you shouldn't think them as literally as physical potentials. But they seem to work. And AlphaFold also puts them to good use. So the question is, why do they work? And the answer is probability kinematics. So you can really get the same type of potentials when you apply this type of probabilistic reasoning. So let's now turn to probability kinematics. So what is probability kinematics? So I'll explain this to you. And then after that, we will see how probability kinematics explains Sippel and explains AlphaFold. So this here is classical Bayesian inference. So we have what we're interested in is we want our posterior, which is the likelihood times the prior, and it assumes that we have some data that relates to our parameter. But suppose that we are in a different situation. Suppose that we have a probability distribution. So here depicted by these equiprobability contours. And suppose that we get unusual information. Suppose that we get information on a partition. So you have these elements of a partition, E1 to E6. So you cut up the support of a random variable, and you get updated probabilities for every partition element. So you basically get evidence, but it's uncertain evidence. It's evidence in an unusual form, and it's not immediately clear how you should apply Bayesian updating to that. So this is where probability kinematics comes in, and I'll give you a very simple example. This comes from the paper Some Alternatives to Bayes' Rule by Diaconis and Zabel from 1983. So this is the reference for statisticians, I think, if you want to read up on probability kinematics. And suppose that we have 4 horses, and they have equal probability of winning in a race, 0.25. But now the probability of A winning is updated to 0.4. So how are you going to update the individual probabilities of the other horses winning? Well, of course, the probability of one of these horses, B, C, or D, winning, if you know that that A loses, is of course 0.6. And assuming here all the horses have the equal probability of winning, so imagine that even though A now has increased probability, you can still assume that all the other horses still remain of equal probability. And then the probability of these 3 other horses winning simply becomes 0.6 divided by 3. So what is the assumption that you've made? So we have actually a partition with 2 elements. So the first partition says A wins. The second partition says one of the other horses wins, which is equivalent to A loses. So the probabilities change from 0.25 to 0.75 to 0.4 and 0.6. So now we have P, the probability that A loses changes from 0.75 to 0.6. The probability that B wins when A loses remains the same at 1/3. And that means that this probability here is equal to 0.2. So in other words, the relative probabilities of the elements within the partitions stay the same. So this is the core idea of Jeffreys conditioning. And then if you write that down in a more general way, so we have Bayesian updating or we have updating, you can call it Bayesian or not, of a prior P of theta, given new information on a partition. And this updating happens as follows. So we have this prior, we have a prior probability over our partition elements, we obtain new information, and we go from this probability over here, so where we here sum over our partition elements, so we replace the previous probability over the partitions with the new probability over partitions. But the marginal probability, so the probability of the parameter given the fact that it belongs to a certain partition, so this remains the same. This is a very simple idea, but it kind of generalizes Bayesian updating to this case. So is it Bayesian or not? There are good reasons to call it Bayesian. Coherence. It generalizes to Bayes, reduces to Bayes when evidence is certain. There's a max end argument. These are all arguments favor of seeing it as Bayesian updating. There's, however, no likelihood, and there's uncertain evidence. So it's kind of a bit of a different way of doing Bayesian updating. And there's actually also Dutch book arguments so that you can also make for for Jeffrey conditioning. Okay, so now we know Jeffrey's conditioning, and let's now see how this applies to our potentials of mean force. Again, we have protein structure. This can be parameterized as a sequence of dihedral angle pairs, or equivalently, you can express a protein as a single point on a hypertorus. So that's the situation we start with. And so Kanti Mardia and my group, we've done a lot of research on this. So application of directional statistics to probabilistic models of proteins, and you see a couple of references here at the bottom. So you can formulate generative models on the hypertorus, for example, coming from fragment libraries. So you just extract fragments from existing proteins and you reuse them. So that was used in the famous Rosetta method. Or you can also just formulate probability distributions on the hypertorus, as we did, for example, in these publications over here. Now, the problem with such models is that they typically only work on a local length scale. They're only going to work for amino acids that are close together. And so you can use these as priors, but they're not going to be very good in predicting the entire structure of proteins. And I can't go into detail about this, but this illustrates the problem. So suppose that this is a true probability distribution over protein shapes, and suppose that you train a typical model using dihedral angles, and you sample from it, you will get this. So this model is valid on the local length scale. So okay, the helix is here, and these strands, these arrows here, the beta strands, they are here. But you can see that the distribution isn't very precise on the global length scale. So locally, you trust this distribution. Globally, you don't trust this. And the problem is, of course, that it's very difficult to put a good covariance structure on these angular distributions. And if you're interested in the topic, so the former PhD student of mine, Wouter Boomsma, recently published an article about this. So take-home message, you can use these models, you can formulate these models, but they will not be good at capturing long-range interactions between amino acids. So how can you still use these models? Well, you can salvage these models by adding a second model that brings in global information. So that corresponds to a multi-scale modeling approach. So the local interactions, you're going to model them using angles. The global interaction, you bring that in with a second probability distribution. So you can use the probability distribution over pairwise distances D. So by construction, if you know the angles, you know the distances. So the distances of a subset of the proteins. So notice that this is a many-to-one function. So there are many values of the find psi angles that give rise to the same distribution. So they pinpoint exactly where all the atoms are, but you can actually have quite a bit of freedom. So you have different conformations of proteins that give rise to the same distances. So we know that D induces a partition on the space of our protein angles. So we can combine the local with the global model using Jeffrey's condition. So here we have the expression that results. So this is our prior. So this is our probability distribution over angles. And you see now our angles are conditioned on the distances. And here we have a probability distribution over the distances. So this comes from a model of angles, an angular model. And this then comes from a probability distribution over distance. And you can get this from graphical models. You can get these distributions from neural networks as AlphaFold did. But where's our potential? We haven't seen our potential yet. We simply have this expression over here. We need to take another step. And we come up with something that we called the reference ratio method. And so we start with this. So this is simply Jeffrey's conditioning. So we update the probability over our partition. And we assume that the conditional distribution remains the same. But now the problem is that this term is not known. We don't have this conditional. We cannot sample angles that are compatible with a certain set of distances. So we cannot use this solution. But what we then do is we simply apply Bayes' theorem to the first factor, to this expression over here. So that can be written like this. So this is simply Bayes applied to this factor over here, to the angular factor. And now we have a marginal distribution over angles that we want here. So that means we have an integral over D. Now, in all cases where our distances are not compatible with our angles, this will become 0. So the only thing that remains is this ratio over here, where we have the angles we have the distances that we calculate from the angles, and we evaluate these two probability distributions at that exact value. So, and remember, these fully determined by the dihedral angles. So if we know the dihedral angles, we know the distances. So these are the only remaining values of the distances that remain. All the other values, they're zero and they disappear. So we can now see that we have this ratio of probability distributions regarding distances times our probability distribution over our angles. And now we basically just simply do a log transform. So we do a minus log for energy over here, minus kt, the log of this ratio over the distances, minus kt of a logarithm of probability distribution of our angles given our sequence. And this is, of course, exactly Sippel's potential of mean force. So now we exactly see where this mysterious ratio comes from. It's nothing else than applying Jeffreys conditioning to this molecular problem and then applying a theorem. So now the mysterious reference state. Where does this come from? Now we know exactly what the reference state is. The reference state is nothing else than the probability over our distances if we would sample these distances from our distribution over our angles. So the reference state is very, very precisely determined. It comes from basically this local distribution that determines our angles. Why is this term usually invisible? People don't really talk about this. And that's because this term was usually traditionally brought in by sampling. So people used MCMC methods. They used fragment libraries or probabilistic models to sample this term, and they would only evaluate this ratio. That's why they only saw this ratio, and they didn't see that we actually had 3 terms involved. How many terms does AlphaFold uses? Also 3 terms. So they're actually using this exact formulation. So we published this in 2010. So that solved a 20-year-long big discussion about potentials of mean force. We were very happy to discover this probabilistic explanation. And it actually took us another 5 years, 2015, to realize that we had stumbled across Jeffreys conditioning. So somebody told us, oh, what you have here is nothing else than Jeffreys conditioning. And that was then published in this book. Here, joint work with Kanti and Mardia. So geometry-driven statistics, where we also finally showed that this is nothing else than Jeffreys conditioning. So now we can conclude the talk, and we go back to AlphaFold. So let's see what AlphaFold is actually doing. So we construct a potential of mean force that can accurately describe the shape of a protein. So let's now investigate what AlphaFold is actually doing in probabilistic terms. So this is the first neural network. So we have the sequence, we have the multiple sequence alignment, we apply a neural network, and we get parameters. And then we generate a potential over our angles. So this will only describe the protein in terms of these dihedral angles. You use a von Mises distribution to express these probabilities. So what's the joint probability of all the angles in the protein? It's nothing else than this long product over here, where each angle is expressed as a von Mises distribution. This is a distribution on the circle. So it's a distribution ultimately on the hypertorus. And the parameters are simply obtained from neural networks. So there's nothing really new about this. People have been using these types of potentials, these types of probability distributions using directional statistics for many years. And then you have the distances. So this is the second component. So the distances are again obtained from a neural network. You have the sequence here, the multiple sequence alignment. You get the parameters. And now you're going to assume that the probability of the distances is just simply a product of the individual distances. So you assume that all of these distances are independent. And I will will come back to this at the end of my talk. So, but notice here that there is quite an extreme assumption being made, namely that all of these distances are independent. And they're, of course, not independent. And now we have the final potential. So how does AlphaFold put these potentials together? So again, neural network. And this time, it's not applied to the sequence. This neural network only takes in as parameters the length of and the position where the glycines are. Glycines are special amino acids. They're very, very small, and they induce special shapes in the protein backbone. So AlphaFold is going to train a neural network that only takes into account the length of the protein and the position of some very special amino acids. It's not going to take a look at the exact sequence. So, and this is, of course, the reference potential. And then the final probability distribution that they create is they have a prior over the angles. They have a predicted distribution. So this is specific for a protein. They have a probability distribution over the distances, again specific for a protein. And then they have this reference distribution. And this basically approximates the probability distribution over the distances if you would just sample from the probabilistic model over the alone. So this one here is tied to this one, and they approximate it using this simple trick by training a neural network that only takes into account the length of the sequence and the position of the glycines. So and this is basically the recipe that AlphaFold uses, and I think it's a very cool story that you have this beautiful piece of Bayesian reasoning that actually contributed to the initial success of a method that got the Nobel Prize to solve one of the biggest problems in biology. Now, and since I am here in Oxford, and I'm actually staying at the Department of Statistics invited by Jotun, and that, if I'm correct, that used to be the Mathematical Institute, right? It's exactly the same building. Now, this is an article that I think is a very, very cool article, and I think it's on my to-do list to kind of apply this to protein structure prediction. So AlphaFold basically assumes that all of these distances are independent. And this is, of course, a very poor assumption. This is a very high dimensional thing, like really high dimensional, and all of these distances are related to each other. And here in this paper, the author is sitting over here, one of the co-authors is sitting over here, Peter Clifford. Is a very beautiful article about the statistics of pairwise distributions, and it's very surprising that you can say so much very precise statements about the probability distributions, about distances that are generated by point sets. And I cannot go into detail here, I don't have the time, but this paper beautifully points out, so if we wish to associate a density function with configurations of points where n is larger than d plus 1, so this is the dimensionality, n is the number of points, we have to describe the configuration not in terms of these n times n minus 1 over 2 interpoint distances, but rather in terms of a set of descriptive quantities taking values in a space of smaller dimension. So one of the reasons that you could imagine that the AlphaFold method could be improved drastically by actually working with probability distributions over distances in these types of spaces, and you actually have quite a bit of results. So I believe that this is highly relevant for the structural bioinformatics of proteins, and it's nice to kind of celebrate this result that has been that originates from Oxford here. And that was my talk. So these are the conclusions. So it took more than 20 years of heated discussion about these potentials. Now we know why they work. They approximate Jeffreys conditioning. They approximate probability kinematics. So the reference state is defined by your local model, typically angles in the case of proteins, and then pairwise distances for the non-local interaction, but it generalizes to all kinds of other properties, and we have actually done work. Good Jeffrey conditioning is a very good use in its 2018 breakthrough, although it did refer to Jeffrey's conditioning. Sadly, it referred to the Kirkwood paper, which actually has barely anything to do with it. And so now that we know about Jeffrey's conditioning, so this opens the way to new, well-justified energy functions, probabilistic models of protein structure in atomic detail. And we know now that you can make very complex distributions from very, very simple components and tie them together using this construction. And it allows you to combine generative models. So, for example, the models over the angles with models that are not generative, like the models over distances. And this is basically the reference here in 2010. So this kind of explained that this type of probabilistic reasoning is underlying these types of potentials. So this is joint work with Kanti Mardia, who is celebrating his 19th birthday this year. I'm very happy to dedicate it to Kanti's birthday. I think so. Yeah, it's all coming together, as you can see. And then some other people who are involved in it. So also John Kent from the University of Leeds, long time on these types of models. These are former PhD students, Walter Boomsma and Jes Frelson. They're both professors in machine learning now. Jesper is working at Novo Nordisk, of course. Somebody has to end up there, so he was very much involved in it when he was still at the Technical University of Denmark. I've also been in contact with Manfred Sippel, was very happy to hear about the relevance of his work for this for the solution of this huge problem, and these were our founders. That's it. Thank you.